Section 11.1 is on page 663, and it talks about parameterization of plane curves. We start off by a definition of a parametric equation. A parametric equation is an equation in which x is defined as a function of time and y is defined as a function of time. Now, for each value of t that you pick, you generate a rectangular coordinate point xy, and as t varies, you're going to pick different values of x and y, and hence you are tracing the parametric curve. Tracing meaning you're going to get direction. A parametric curve has or possesses an initial point and a terminal point. Anytime I see graph a parametric equation, direction must be included. Without direction, it's not a parametric equation. So the difference between rectangular coordinates and parametric equations, the graphs are identical, except parametric equations possess direction, something that we must get out of the way. Now, I'm ignoring all the directions in the book. I'll show you the directions in the book and what it says, and we'll go from directions in the book. Really reads 1 through 18 gives parametric equations and parameter interval for the motion of a particle in the xy plane. Identify the path by finding Cartesian. Cartesian is rectangular coordinates. Graph the Cartesian coordinate. The graph will vary, blah blah blah. Indicate the portion of the graph traced by. All of that we're not going to actually worry about. The only thing I'm going to worry about in this case is I'm going to state find the Cartesian coordinates, meaning eliminate t out of the equation. If x is a function of time and y is a function of time, you could solve for t in one of them and substitute in the other. You're better off getting y as a function of x if possible. Sometimes it's not possible. And sketch the graph of the parametric equation. That means get me direction. The reason you want to eliminate t out of the equation, you don't want to plot points and guess how this graph look like. Instead, you want to get y as a function of x, and since we know how to graph almost anything by now, that should be an easy graph. And once you get the graph, you pick a couple of values of t and figure out the direction. So, starting with x equal negative radical t and y equal t, and t is bigger than or equal to 0. First things first, I could take y equal t and substitute that in there. X equal negative the square root of t. Negative the square root of y, apologies. Now, do you know what that means? Well, x equal radical y is a graph that looks like this. That's because y equal x squared, but it's only the right half of the parabola. So in this case, I could say, well, look, x squared equal y, but it is the left half. So at 0, 0, when y equal 1, x equal 1, right? Oops. And when y equal 4, x equal 2. That's really how the graph look like. Now I need direction. All what I have to do is pick a couple of values of t. That is, let t equal 0. This is where I am right now. I am at the origin. And in 1 minute time, where am I going to be? I'm going to be at, if I put t in there, negative square root of 1 is negative 1, 1. I am going to be right there a minute from now. That means the direction is running this way. Do not mix things up. Do not take the actual direction from the Cartesian coordinates. It doesn't work. You always need to plug in a couple of values of t to figure this out. I forgot to mention that this is on page 669. So let me start with number 4. On number 4, again, they're limiting t. Not to worry, I would work on, if I could get y as a function of t, that would be wiser because I am used to that, nothing more. if I could take this and substitute that right there, y would equal 2 into 3 minus x over 3. That is y equal 2 into 1 minus x over 3. That is y equal 2 minus 2x over 3. So I know this is a line that has a y-intercept of 2, runs 2 down, 3 to the right. So I know the infinite line really looks like this. But since they're limiting t, I should know that it's not going to be the infinite line. It's going to be a piece of it. Which piece? And if I take t equals 0, remember it goes in the original equation right there and right there. 0, I'm at 3, 0. I'm right here right now. And in 1 minute time, when I put 1 in there, I'm going to get 0, 2. I'm going to be here in 1 minute. So I'm only tracing this piece of the line. So the rest, either you cross out since you're using a pencil, or you erase, either or. And the direction is clear. I'm not liking that much, but it's okay. I'm going to go on. Alright. And if I look at the next set of problems, well, let's look at number 6. 6, anytime I see trig, I'm going to be thinking of the identities, just like we did back in chapter 8. So I'm going to use the most famous of them, the Pythagorean. That works on almost all of those. So that's what it seems to do. If I square both sides, I get x squared equal the cosine squared of pi minus t, as long as the angles are the same. And if I square both sides, I'll get y squared to equal the sine squared of pi minus t. And now if I add, the left side will be x squared plus y squared. The right squared, sine squared plus cosine squared, is a 1. I know that's a circle with a radius of 1. So the circle is right there. Let me exaggerate that a bit. Let's say that's a 1. So this is a circle with a radius of 1, but I'm only tracing a portion of that circle. At t equals 0, if I put t equals 0 right there, that's going to be cosine of pi, which is negative 1. And sine of pi, which is 0. Negative 1, 0. This is where I am at t equals 0. And in pi over 2, pi over 2 minus pi minus pi over 2 is pi over 2. That's a 0. That's a 1. I'm going to end up being right there in 1 minute time. So I'm moving in this direction. And at t equal pi, pi minus pi is 0. Cosine of pi is 1. And that's a 0. So I'm only tracing the upper half of the circle, but not in the traditional rotation, in negative rotation. So again, you plug in the t values in the original equation to figure out the orientation. Do not use what you think you know from trig or algebra. Same deal with this. When I see trig, as long as the angles are the same, I'm going to make use of the Pythagorean identities. Sine squared is going to equal x minus 1 squared. And here, y plus 2 equal cosine of t. So cosine squared of t is actually y minus 2 plus 2 squared. And if I add those, 1 will equal x minus 1 squared plus y plus 2 squared. So again, it's a circle. But this circle is centered at 1, negative 2, right there. And the radius is 1. So I'm going to move 1 in all directions. And the circle will look something like this. Now, I'll go back. At t equals 0, where am I? Well, plug 0 in, that's a 1. Plug 0 in, 0 right there. That will make this a 1 minus 1. Minus 2 is negative 1. So 1, negative 1, I'm right here right now. At t equal pi over 2. sine of pi over 2 is 1 plus 1, that's a 2. That's a 0 minus 2 is negative 2. 1, 2, negative 1, negative 2. I've just read that much. And obviously at t equal pi, I know where that's going to end up being at. That's a 1, and that's a negative 3. 1, negative 1, negative 2, negative 3. So I'm tracing the right half of this circle again in a clockwise rotation. A couple more to go. Now I'm debating if I could finish this in one section, and it looks like I can. So here, again, I'm going to make use of identities. I am going to square both sides, and I'm going to get secant square root of t. You could use cosine, or you could say, you know what, I know what that is. This is tan squared of t plus 1. So again, I could use substitution. I could have used elimination. You could use whatever you want. If that is my y, so this is x squared minus y squared equal 1. Well, I know how that looks. We just did that. And since the negative is on front of the y, so it looks like it's one of those, except they have a restriction on t. Notice t cannot be negative pi over 2. So let's go from negative pi over 4 to 0 to pi over 4. And that pretty much should give me a very good idea of how that works. And remember, I go to the original. If I plug in negative pi over 4, secant of that would be negative radical 2, because secant is 1 over cosine. Positive or negative makes no difference. But the tan of negative pi over 4 is negative 1. Negative 1, negative 1.4, negative 1. Here I am. At 0, if I put 0, secant of 0 is negative 1, because cosine of 0 is 1. And that's a 0. Negative 1, 0, I'm right there. And negative radical 2 and 1. Negative radical 2 and 1. So I'll know that I'm tracing this piece of the graph. I don't like that. Let's go with... And I know that the direction is actually right there. There it is. Now, I'd like to look at the next problem. I want to work backwards. Given, of course, I don't need to graph this, but it helps to see the graph. If I run from negative 1, 3, negative 1, 1, 2, 3, to 3, 1, 1, 2, 3, I'm sorry, negative 2, 3, negative 2. The line runs right there. Okay, so I noticed that the slope of the line I could figure out either by using the formula or counting down, right? 1, 2, 3, 4 down, and running 1, 2, 3, 4 to the right. So the slope of the line, actually I messed up on the graph. It's more like negative 1, 1, 2, 3. The line is actually running right there. So actually 1, 2, 3, 4, 5 down. So the slope is 5 down and 4 to the right. That's m. And if I take one of the points, let's say I take the first point, y minus y1 equal m into x minus x1. Y equals negative 5 over 4x minus 5 over 4 plus 3. Y equal negative 5 over 4x plus 12 7/4. If you get the equation that way, it's very easy to write the parametric. If y is a function of t, let x equal t, and y is automatically negative 5 over 4 times this t plus 7/4. There it is, whatever that is. And the limits on x are very simple to find. If I let x equal t, then here it is. that would be from -1 to 3, and that'll work. And there's the homework.